So today we're going to talk about reliable data transmission. Over noisy channels. So the basic setup we have is, well, we put, in the first lecture I showed you the overall block diagram model of the data transmission problem. And now we go back to that, and basically we're going to use all of these blocks. An encoder, a channel, and a decoder. And coming in on the left over here we have a source of messages, a message source. And coming out from the right over here we have a message sink or a message user. So when we talked about source coding, what we said was that the channel was trivial. There was no noise. It simply passed symbols from the encoder directly to the decoder. Therefore, the problem was, how do we most efficiently represent the messages? In our current problem, reliable data transmission over noisy channels, we're going to say that the channel introduces distortion. Therefore, errors can possibly be made in the transmission from the encoder to the decoder. So this we see in practice all the time. We're going to say the message belongs to some set M, where M is a set from 1 up to, or correction, we're going to call this set W. And the elements of W are numbered from 1 to M. So the encoder takes a message, one of these discrete messages, and maps it to some channel input alphabet. We'll call this S sub x. So one example would be binary. We could map the message, some discrete message in this set to binary. So e.g., it need not be true, but for example, Sx could be binary 0, 1. The encoded version, so we will map some message into various elements of this alphabet. We will then pass Sx through the channel. The output of the channel is in some alphabet Sy, which need not be the same as Sx. Sometimes it is, but it need not be. So we could have a binary input, binary output channel, in which case Sy is also 0, 1. There are many practical examples where our input is binary. So for instance, we were attempting to send bits, and the output is continuous. So it's corrupted by some continuous valued noise, such as Gaussian noise. That's a very common example. Finally, the job of the decoder is to take these channel outputs from this alphabet and map them to some estimated message alphabet W hat, set of messages W hat, where we will allow, okay, a W hat must contain all of the original messages in W, because if it's possible to send any of these messages, then it must be possible to receive any of these messages. But we're also going to allow W to contain the element 0, which is not in W. The interpretation of the element 0 in W hat is decoding failure. So, two possible error events can happen here. The idea is if I choose a message from W and send it, I want the output over here to be the same as the input. So there's two possible ways that can go wrong. The first is if I put in a W over here and I decode it to some other element within W that's wrong. That wasn't what I put in. So that's very bad. That's an undetected error. So an error occurs and I didn't realize it and I'm actually mapping it to the wrong message. The zero, the interpretation is I have a message input here and the output is 0, which is not something that was in W. And that's basically the decoder declaring that it doesn't know how to interpret the channel outputs and can't map it back to something to some valid message. So that's basically a detected error. So here the decoder is basically giving up and telling you that it doesn't know. So that's actually a good kind of error because it's one that can be detected. The bad kind of error, or a less good kind of error, is, it's not a good kind of error because you didn't get the message through, but it's good in the sense that you know that you didn't. The worst kind of error is when you transmit something and you think it's something else as a receiver. Then you're not detecting the error. So, we're going to assume that the distortion is in some way stochastic. So that means that in the channel there is some probability of outputs given inputs, like so. So in other words, given that a certain element x was sent, where x is in Sx, what's the probability that y is observed? Where y is in Sy. So this must be defined for all pairs of inputs and outputs. And it must also obey the usual rules for probability. So the sum over y of this is equal to 1. We're going to make some assumptions here. We're going to make these definitions considerably more formal. This is just a quick introduction.